Welcome to homework.
Hello everyone, today we're doing chapter 29, problem 64, and this problem asks us to draw out the organic product formed in each reaction. So let's start with A. So we have valine reacting with methanol in acidic conditions. So we know that there's going to be an esterification reaction occurring. So we know that this carboxylic acid is going to be converted into an ester to give us our product. This methyl ester with our valine amino acid. In B, we have this phenyl protecting group, which remember in previous examples, we showed that this protects the carboxylic acid and makes it inactive for any sort of chemistry to occur, such that only the amine side will stay reactive for further reactions. So with this, your alcohol here will act as a nucleophile and attack the carbonyl carbon of the carboxylic acid, making a new bond and kicking off water in the process to protect your carboxylic acid and, in essence, inactivate it from any nucleophilic attack. In C, we have Boc anhydride and triethylamine, and we have the amino acid glycine here. So we know that, just like before, Boc anhydride is also a protecting group, but now it protects the amino side of it. So if we were to do this reaction, we would have a Boc-protected nitrogen, amino backbone, and this is glycine. In D, well, what happens if we take the product of B and C and add DCC? And what is DCC? Well, the DCC is the amide bond coupling reagent. So in product B, we have an inactivated carboxylic acid, but we have active nucleophilic nitrogen. And in C, we have an inactive nitrogen, but we have a reactive electrophilic carboxylic acid. And by coupling those with DCC, the amide bond coupling reagent, we're going to have an amide bond being formed between this nitrogen and this carbon here. So if we see, then obviously this would be the N-terminus. So we'd have a Boc-protected N-terminus, a new amide bond being formed, and that's C-protected, C-terminal protected carboxylic acid. In E, what we're doing is we're taking this kind of protected amino acid and we're adding hydrogen on palladium carbon. So hydrogen on palladium carbon is actually a deprotecting catalyst that selectively deprotects the C-terminal protecting group. And the C-terminal protecting group in this case is that phenyl group that we used here in B. So we're going to selectively deprotonate that or deprotect that without touching any other groups on the molecule. So we're going to deprotect this to regain our carboxylic acid. And we get our valine back. Now F says starting material of E, and we're adding HBr. So we're adding a strong acid with the starting material of B. So we know that an acid-catalyzed hydrolysis is going to occur, such that we're going to regain our free amine and our free carboxylic acid terminals. So we're going to regain our free amine and the free carboxylic acid ends to gain the original amino acid valine. Now G says a product of E with this fluoroacetogassic derivative, trifluoroacetoacid, acetic acid, and then we have a product of E, which is this, with trifluoroacetic acid. So it's once again acidic condition. So once again, we're going to have acid-mediated hydrolysis to regain the same product as in F for G to regain the original amino acid valine. And last but not least, in H, we have the phenylalanine being reacted with FMOC chloride and carbonic acid and water. And we know that obviously FMOC is bound to chlorine, chlorine being a good leaving group. And then we have both the nucleophile and electrophile on the amino acid. So if we're reacting this with something with a leaving group, then this must be the electrophile, meaning that the amino acid must act as a nucleophile, meaning that the nitrogen will most likely do an SN2 backside attack with FMOC to FMOC protect itself and kick off chlorine in the process. And that gives us a product in H.